Now, in this last part of this series of videos, we're going to talk about small oscillations. So, almost any chemical system, or better, almost any chemical motion or motion inside a molecule usually is approximated as a small oscillation around a equilibrium position. It may be stretching, it may be bending. In any case, it's usually a small movement around an equilibrium position. And usually this movement will be approximated as an harmonic oscillation. Here we will have a quick overview about the classical harmonic oscillator, but of course many chemical problems might need to use the quantum mechanical ones, but not everyone. For example, every time you are doing a classical molecular dynamics, you are using a classical harmonic oscillator. So, let's start. How do we approximate a small oscillation? Small oscillation, so usually it will be something like a particle bound to a wall with a spring in the middle, so attached to a spring that is attached to a wall, or a particle that is on a pendulum. So how could we describe a particle attached to an ideal spring or an ideal pendulum doing small oscillations? So, if we have, for example, this particle attached to an ideal spring, we will have the equilibrium position q0 and the actual position in time q. So we will have to know how we might express the potential energy of this system. It's quite easy because we are doing a Taylor expansion. Very easy. So u of q minus u of q0 will be equal to the first derivative according to position in the equilibrium position times q minus q0 plus the second time derivative of exactly the same thing, q minus q0 squared. Then we could go on, but we are stopping ourselves here. But this is a minimum, so the first derivative will be 0. And this, of course, in the equilibrium position, this will be a positive constant that we will call k. And k is greater than 0 because in a minimum, the second derivative is always bigger than 0. Okay, so if we are deciding to call q minus q0, so the displacement from the equilibrium, as x, we can rewrite our potential energy as the potential energy according to x equal to, oh, I forgot 1/2 here. Okay, I forgot to put 1/2 here because of course it's 1/2. 1/2 k, that is our constant, x squared. So as k is greater than 0, our potential energy is nothing more than an upwards parabola centered in the origin, and so it's symmetrical. There is no difference in which direction I'm choosing. It will in a perfectly symmetric way go up when you go away from equilibrium. Now we have to write the Lagrangian of the system. Now the first question is, how is the kinetic energy? In general, it will be 1/2 a function of coordinates q dot squared. But as we are doing small oscillations, we can approximate a as a constant and actually approximate it to the value of a in the equilibrium position. So 1/2 a q0, it will be almost equal because it's an approximation q dot squared. For writing it shortly to be faster, I will call it simply 1/2 m q dot squared. Of course, this is not the mass, at least if we are not in a Cartesian coordinate system. So remember, this is not the mass. As we're actually using x instead of q, we will rewrite the kinetic energy as 1/2 mx dot squared. So at this point the Lagrangian will be 1/2 mx dot squared minus 1/2 k x squared. By solving the Lagrange equation, we will get our equation of motion. That will be mx double dot k x equals 0. That can be written as x double dot plus omega squared x equals 0, where omega is equal to the square root of k divided m, and omega is what's called angular frequency or frequency. So that's the frequency of our oscillation, and that's the reason why we write it in this different way. And this is the equation of our oscillation, of our harmonic oscillation. Now this is a differential equation, so we will have to solve it. So actually I'm going to skip the solution and arrive directly to the solution. I will skip the process. So it can be written as a cosine of omega t plus some kind of phase. So it will be an oscillation. So cosine, where I will have an amplitude, I will have a phase. Of course I will have my time dependence, and depending also on the frequency. This can also be written, in some cases it's more useful, as the real part of a e at the I omega t. So as a complex number where a is also a complex constant. So you, depending on the problem you're solving and on what you have to do, you can use the real version or you can use it as a complex number, and then remember that x is actually the real part of it. So now what we have seen until now is if we have no other force, no external force, but there are plenty of situations in which we might have some kind of external force. Let's see how forced oscillations work. And actually, in what we are really interested is resonance, but we will see it. Now, we might have some kind of force that depends on time, some kind of time dependence. So the potential energy can be rewritten as 1/2 kx squared minus x f of t. We have put f only in the first part of the Taylor expansion because already on the second order it would have been given a very small contribution, as we are talking about small oscillations. Of course, this wouldn't be true for big oscillations. So the Lagrangian will be 1/2 mx dot squared minus 1/2 kx squared plus x f of t. So the equation will be x double dot plus omega square x equal to f t divided m. So this is again a differential equation, but it's not an homogeneous one anymore. So in general, if I have some kind of force, this is the equation I have to solve. And of course I will have to know what kind of force I have. Now things become quite interesting when I start having a periodical force. So if I have some kind of periodical force, I can have two different kinds of solutions. One if the frequency of the force is different from the frequency of my oscillation. In this case I have no resonance, and the solution is in the form of so this is our old solution at which we have to add. So this is the solution in case we don't have any kind of resonance. So if we are going to have some resonance, so the frequency of the force is tends to the frequency of our small oscillation, we will start having a kind of resonance. So we will have a solution in the form of, so again the previous solution plus and as you can see, in this case I will have a linear dependency on time. So the amplitude of my oscillation will grow in time, grow and grow and grow in time. And this is what we call resonance, because of course the amplitude has to grow. This linear growth is true only for small oscillations, so if this resonance keeps going on, this force keeps existing, we will go out from the linear range and go in a non-linear one. But in this case it's not a small oscillation anymore, and our model wouldn't work anymore. But for small oscillations we have a linear increase in the amplitude.